Let us quickly motivate the definition of places via the interaction between geometry and algebra. Let us first consider the case of Riemann surfaces. For any Riemann surface X, one can associate its ring of meromorphic functions. We can then ask the natural question: is it possible to reconstruct the space X from its field of meromorphic functions? The answer is yes, and that's where places come in. More generally, one could ask, given a ring A, would it be possible to construct some kind of space, some kind of geometric object whose ring of function is actually A? This is a question that leads to the development of scheme theory. The geometric space of choice is just gonna be defined to be the space of all prime ideals of A. On it, we can put a topology and even something called a scheme structure. Such a geometric object is called an affine scheme. Now, imitating the construction of manifold, we can patch together affine schemes to get an object called schemes. For an irreducible scheme X, we can also define the notion of a function field of X. Now, in the case when Kx is a function field of one variable over K, i.e. it has transcendence degree 1 over K, then again we can recover the geometric object X from Kx as follows. Observe that Kx contains the following two subrings of the field of rational functions in one variable over K, namely the integral closure of the polynomial ring in one variable in Kx, as well as the integral closure of the polynomial ring in the variable T inverse in Kx. And the space X is just going to be the scheme obtained by gluing the spectrum of A and the spectrum of B in a reasonable way. The elements of spec A and spec B in this realization of X are called by definition places of the function field Kx. Thus we see that places give a geometric realization of a function field in one variable. Now let us give a formal definition of places. We'll first define it for the case of number fields, and then we'll look at function fields in one variable. A finite place for a number field K is just gonna be a non-zero prime ideal of OK. Thus, the set of finite places of K is just the prime spectrum of K. Now, an infinite place of K is any real embedding of K. The relationship between finite and infinite places is that we can think of a finite place P of K as an embedding from K into the completion of K at P. We'll define this completion in upcoming videos. Now, for a function field in one variable, we can imitate the previous discussion to give an extrinsic definition of places of K. This definition is extrinsic because we need to fix an embedding of kt inside K. Once that is done, then as before, we can define the ring A to be the integral closure of the polynomial ring in the variable T inside K, and then B can be defined to be the integral closure of the polynomial ring in the variable T inverse inside K. Then the finite places of K are defined to be the non-zero prime ideals of A, whereas the infinite places of K are defined to be the non-zero prime ideals of B containing the ideal T inverse. Now, as we have mentioned, the disadvantage of this definition is that it's not intrinsic. The more intrinsic way to define places of K is as discrete valuation on K that vanishes on the units of the base field. And we'll define what that means in the next video.